Hello everybody. Let's take a look at Chapter 3, which is Scientific Measurement and the metric system and all that fun stuff. And along with that is the concept of significant figures. Okay, so this is kind of a big concept of how do we deal with numbers in chemistry. So say, for example, we're taking a look at a line, just very simple example, that we're taking a look at a line like this. And we need to communicate to somebody across the planet of how long is that line? Now, we might use this for industry, we might use this for replicating an experiment, we could use this for lots of ways, but remember that science is a global endeavor, and so we are going to be communicating as scientists to convey ideas, to convey the next level of questions and so on, and so we need to make sure everything that we do for measurements and data is translatable to everybody else and everybody is on the same terms. So we have a line that's about this long, and so we might have different levels of maybe the scope of the experiment or whatever we need to do. We might have different tools of how to actually measure that line. So in science, we deal with numbers as conveying meaning. Now, a significant figure, if something is a measurement that is a number or a factor that somebody needs to be paying attention to. The concept of significant figures is that we have a measure. It tells us what the tool is that we're using, as well as what somebody's professional opinion as to an estimated value. Okay, so it's somebody that's trained in the experiment, that's trained in the data collection process, in what do they anticipate, and a conveyance of what is the next degree of accuracy. So if we're going to take a look at a line like this, for example, and we're going to measure this, could be for volume, it could be for length, it could be for lots of different things, and we used a tool like this. Now this is just kind of a standard like ruler that we have, and say this is in centimeters, the metric system, and so on. We're taking a look at this, and everybody can agree that this is the 1 line, the 2 line, the 3 line, and so on. But this line, if we were to actually kind of transfer this down, if we're going to go from here to here, and I'm going to translate it into that ruler, I could see, oh, wait a minute, that is a line that we know everybody can agree is at least 3 centimeters long, but it's actually a little bit closer to 4. So if I was going to measure this line using this particular tool, I would maybe say that is 3.7 centimeters. Okay, now somebody else might use their own opinion and say we can all agree that it's on 3, but it might be a 3.6 centimeters. Or somebody else might say that it's a 3.7 centimeters. So you see what we're doing here is we have a measuring tool that everybody can agree where that 1's value is, and then this next number right here is an estimated value. Now it's important because it does tell a person, the reader, whoever's looking at these numbers, that the number is going to be closer to the 4 than it is the 3, but it gives us a ballpark. Okay, now if we're going to translate that same scenario down to a different measuring tool that is more expensive, it is more time intensive, and we see, okay, so, according to this, if I have my lines all matched up and everything, let's say that I measured it down, we can all agree that it hit the 3 line, and if you look, 1, 2, 3, 4, 5, 6, 7, 8, let's say it hit the 8 line. We could all agree upon that, okay? So everybody is going to get to that exact decimal level. And so then the reader or the scientist would actually go through and say, okay, how close is it to that 0.8 or the next level, which is a 0.9? So then they would put in, maybe that's the estimated value right here is a 3.87. So you see the difference? It's the same line, and then all of a sudden we have 2 different tools with which to measure that line, and so we have a different level of accuracy. So here somebody measured, everybody would measure for sure 3.87 3.8, and then the value that is the estimated is this 0.07 here. Okay, now what if we were going to translate that to a tool that was even less specific? Okay, now again, this is you might look at that and go, well, that's kind of a dumb scenario, why would we do that? Well, maybe we're doing something in a procedure that is in broad scope, so we don't need to go down to the hundredths. So why would you possibly do that if all we cared about is how close was it to the 1's place or whatever? Maybe you use a tool that looks like this. It's a lot cheaper for sure, and it is one of those things that's a lot more time efficient as well. So we use our values, okay, we kind of do the same thing. Okay, it's about there, and so it's about there, so I'm going to say, maybe this one's going to be about a 4-ish, okay? Nobody knows for sure if it's going to be 4. We know, we could all agree it's not at a 0 and it's not at the 10, so we know that it's a degree, it's between 0 and 10, but we understand as scientists when we see a number reported at this is an estimated value. Somebody else certainly might measure that as a 5, somebody might measure that as a 4, and they're all good because that is an estimated value. So this gets into the concept of significant figures, okay? Significant figures exist to tell the reader how close did they measure this, okay? To what degree, what type of tool did they use, how nitpicky do we need to be in those values. So I would say certainly we would take and estimate this value. That is an important value to recognize, but we would say that with a significant figure, that this number that's reported out has 2 significant figures. Everybody can agree that it's to the ones place, and then the tenths place is going to be estimated. Now this one would be as 3 significant figures because we went down to the ones place and the tenths place. Everybody could agree on that, and this is an estimated value. Still valuable, but it is one of those things that it's kind of one of those soft numbers, okay? We understand when we're doing math that this number is a soft value. Now we also see when we have 1 significant figure, okay, this is an estimated value. It's important, but this value is one of those, again, soft numbers. So then when we do things in science, when we're taking a look at multiplying things or adding things, this is where different rules come in. Say I was going to take a measurement that we said that was going to be 3.7, and we were going to multiply it with something that was 3.87. Well, you're going to multiply this. It's not like math class where you just take 3.7 times 3.87, you're going to get a value. We're going to instead say, well, we're going to acknowledge this is a soft number. It's subjective, okay? We can all agree that this number is locked. There are 2 numbers here that are valuable. This one has 3 numbers that are valuable, but this one is a soft number, okay? But this is the weak link right here. So in class, I always say it's kind of like when people or friends are get together and they order a pizza, and you go around and say, okay, how many pizzas do we want? There's 6 of us. I don't know. Do we get 1? Do we get 2? Kind of depends on how much money you have, right? So if you're going to be calling up the pizza dude and kind of say, hey, this is what I want, you kind of go around to your family of friends or whatever, and you kind of say, okay, you got 6 of you. How much money do you have? And a person might say, well, I don't know. I got somewhere around $1. Okay, somebody else might say, well, I've got $3.25. And somebody says, I don't know, I got somewhere around $10. Okay, so if you think about it in that way, here's a person that says they have about $1, a $3.25, and 10. Who do you think is going to be the most reliable? Okay, if you just simply add this up, we got $14.25. You probably have enough for 1 large. Okay, unless you go kind of find some specials and do your thing. But if you have $14.25, is that very reliable? In math class, you'd say that you have exactly $14.25. But remember the scenario, and this is where significant figures comes in. We're saying these numbers, this last number reported, reveals its level of accuracy. Somebody said that they had $1. Well, that could be $1.10, or that could be 90 cents. Or even 80 cents, okay? So it's somewhere around $1. Now, if somebody says they have $3.25, well, we understand in science, well, that's $3 for sure and 20 cents for sure, but this might be 4, this might be 3.26, it might be one of those other things. Now, this person says, I got somewhere around $10. Okay, now if you're anything like me, you've got friends that always say something like that when we know in reality that they really only have like $8. Or maybe $7. Maybe they have $12 and they're just holding out on you. But we know that that's going to be a soft reporting. Well, look at the difference between this. If you have maybe this $10 turned out to be $7, and it was a $3.26, and it was actually 80 cents. Well, wait a minute. We're talking $10 and what, 34 cents? $10.34 compared to your $14.25. Well, that's a huge difference. And so you see why we have different values that we report out. Now, there are rules that dictate. Now notice that I added, and actually I cheated a little bit because I just kind of said, gave you some soft numbers to work with, but there are rules that dictate how we add and subtract and what do we do with those values and so on. I wanted to just show you, for example, what scientific measurement, how you measure using these tools. You see each level of decimal level and you take it one more place. Here we see this goes from the ones and the tenths, and so you'd estimate to the hundredths. Here we only know the 0 value and the 10 value. Okay, so we don't see anything to the ones, so that we know that's going to be an estimated. And sometimes you even see this little mark in here. And don't be deceived, because I see a 5 there. That doesn't mean I know where 4 is. That doesn't mean I know where 3. That 5 is actually just to help you estimate. It is not an accurate 5 by any means. Okay, now let's take a look at one more thing, which deals with, and I already mentioned this because I used the units of centimeters. Let's take a look real quick on another aspect that we agree on within the scientific community is what units are we going to be using, okay? So this is the SI system, the metric system, which in the United States is always going to be a little bit scary because it's something a little bit different and something that we think seems, so foreign that we wouldn't do it. But it is actually the best way to communicate as scientists, and it's also, the reason it's the best way is because it's based on a base 10. Okay, so the base 10 means this. We have every tenth of a unit. Every tenth, every line here is a tenth of a unit. So for example, if I had 100 centimeters, the question is, how many decameters is that going to be? Now notice I have a capital D here versus a lowercase d. Well, because this is a base 10, I do this. 100 centimeters, here's my decimal point. I'm going to move it 1, 2, 3. Now the square represents like the meter, the gram, or the liter, kind of the base unit there. So everything is going to be kind of going to the right or to the left of that, and we're just simply balancing a decimal. So if I'm going from centimeters, 1, 2, 3 times to the left, 1, 2, 3 times to the left, that becomes 0.100 decimeters, or decameters, I'm sorry, decameters. If we had something like 37.8 hectometers, and I want to know how many millimeters that is, well, take a look at what we're doing. Here's where my 37.8 is. Here's my decimal point. If these reflect a base 10, it means I'm going 1, 2, 3, 4, and 5. Okay? So I'm going to be moving that decimal. I'm going to be dividing, multiplying by 5. I'm going to be moving it over to the right 5 times. So here's my 37.8. 1, 2, 3, 4, 5. And I put that back. And so now you just fill in your zeros, and you can very easily, oops, I'm sorry, I missed that one. We can very easily convert. Now that's a lot easier than somebody that's going through and saying, if I had, for example, 13.7 miles, and I wanted to know how many inches that was. Eesh. Better grab your calculator, better know some fancy conversions and so on, because this is a much more complex thing, because you have to figure miles to feet and then feet to inches, and even if you do know those conversions at the top of your head, you still don't really understand how you could do that without moving a decimal and picking up your calculator. So we use a base 10 system in the metric system to convey that information, and our numbers have meaning, but also how do we convert and work within those things to fit our different parameters. So that's just a quick how-to on how to figure out, measure things, what significant figures are in essence, and then also dealing with the metric system itself. Now you notice we have a little issue here with zeros. Okay, zeros become a big issue because zeros sometimes have meaning and sometimes they don't. So let's say, for example, I have 0 to 10. We have a measurement here. We have another tool that, let's just change the scope on it. We know every tens. Don't get too hung up on, the precision of my placement of all these things. We're just kind of conveying that. Versus, here we know every ones. and so on, okay? So here's 9, here's 10, and it keeps on going to 11, 12, that kind of thing. So what if I wrote a number that says that we had 500 centimeters? What kind of measuring tool did we use? Now this is kind of a tricky question because I have 500. So this means that everybody can agree that there's, in the hundreds place, we would see 5. So we could go this and keep on going if we wanted. But did we actually have a tool that reflected down to the 1 or tens place? Did we have a tool that goes down to the ones place and so on? So we need to understand some things about these zeros, okay? So zeros become an issue. So here's the rule. If they are placeholders, like we see in this example, they are not significant. Okay, so we're saying that everybody can agree we've got this, but we don't know, for example, the tens place. This is just the rule. So we can agree that there are 0 thousands and we have 500s as the estimated value. Okay, this is kind of weird. That's an estimated value because those zeros are considered placeholders. In other words, this 500 can be written as 5 times 10 to the second. All of a sudden the zeros disappear. So we have another scenario of placeholders where we measure something to be 0.05. Well, wait a minute. This is a kind of a weird thing. This is a placeholder 0 because I can write 0.05 as 5 times 10 to the negative 2. And so all of a sudden, it just disappeared. So zeros as placeholders are not significant. Okay? Now let's take a look at another scenario. Another scenario is a value reported out is going to be 502. Here's another 0 right here. Is that 0 a placeholder? No, because we would see a value after it as well as before it. Now everybody would agree that this 500 is measured. This 0 would be measured, reflecting that there's 0 tens, and this is somebody's estimated value right here. Okay, so that means that somebody might have a 503, somebody might have a 504, people might have a 501, and so on. So we can all agree it did not hit that tens place. So this is what we refer to as a trapped 0. Okay, trapped zeros are significant. Everybody can agree that somebody actually measured that. Okay, so that's another scenario where zeros in this case are significant. Now let's take a look at another one. 0.00500. Whoa, what a weird number. These are placeholders. So the question is, what about these guys right here? Why would anybody write that? And in class, I always say, you're going to be that kid on the playground that really says, I measured something out to be 0.005000000. You're just going to get pummeled. Why would you say something like that? Unless you actually measured it. And so what we see, if we're going to translate this to scientific notation, you would keep those zeros because somebody actually took the time, 1, 2, 3, to measure those zeros. Now this guy's trapped. To be clear, this guy would be my estimated. And so somebody else might say, I think that was maybe a little bit closer to the 1 or maybe closer to the 2 and so on. We can all agree that we never hit the 1 value there. But this is the idea behind significant figures as well. When we see trailers after or rightmost zeros after a decimal point, rightmost, not these guys. These guys are placeholders. These guys right here, those are going to be significant because somebody took the time to actually physically measure them. So what would this tool be? This would be something that we know the tenths and the hundreds and the thousandths, the 10,000ths, and so you'd actually take the time to measure the 100,000ths and report that out. So this is the concept behind significant figures, how we actually physically measure, and the rules that govern that. Okay, and there's another tutorial coming up that deals with how do we do our math with it and so on. Now I also gave you a little bit of an information about the SI system, the System International. The international scientific community uses these values as part of the SI system and how to do some basic conversions. So that's in another video tutorial. I just wanted to show you measurements for the big part and how that fits into everything else within this chapter.